next topic we can see is the randomized algorithms. So, what is meant by randomized algorithms? Randomized means that algorithm that uses random numbers to decide what to do next anywhere in the logic is called randomized algorithms. So, it will be making the decision based on some random number. For example, in randomized quicksort, we pick the pivot element by randomly shuffling the array. Typically, this randomness is used to reduce the time complexity or space complexity in other standard algorithms. So, randomized algorithms, one example is a randomized quicksort, randomized version of the quicksort. So, randomized algorithms are mainly classified into two categories. So, first one is, so it will be depending on some random number. So first type is Las Vegas algorithm and second type is a Monte Carlo algorithm. In Las Vegas algorithm, even if it depends on the random number generation, will always produces the same output for the same input. Whenever the algorithm runs for the same input, it will produce the same output only. But the execution time of the Las Vegas algorithm depends on the randomizer. But for the same input, it will always produce the same output. Randomized version of Quicksort is an example of Las Vegas algorithm. But in Monte Carlo method, it produces the correct or optimum result with some probability. The output of these algorithms may differ from one run to run for the same input. If we give the same input for a Monte Carlo algorithm, it will produce different outputs at different time according to the generated random number. But the time is almost same. Running time is almost same. Okay, now the example for a randomized algorithm is the randomized version of the Quicksort, which uses the Las Vegas randomized algorithm. So Quicksort, already we have learned Quicksort, what is meant by Quicksort. So in Quicksort, the division of array into two subarrays is made such that sorted subarrays need not to be merged later. In merge sort, after dividing and sorting, the subarrays need to be merged, but in Quicksort, the merging can be avoided. So how this Quicksort works, you can see. The main principle of Quicksort is a partitioning method. So in Quicksort, for example, if we consider an array, suppose this is the array to be sorted. For example, 10, 15, 1, 2, 9, 16 and 11. So here 6 elements 0, 1, 2, 3, 4, 5, 4, 5, 6. Total 7 elements are there. So suppose this is the array A. So this has to be sorted using Quicksort. So first we will select a pivot element and name it as P. Pivot element from this array, and based on the pivot element we will partition this array into two halves. So mostly the pivot element can be the first element, or it can be considered as the last element, or it can be somewhere in the middle element also. In this case, we will consider the first element as the pivot element. First element is considered as the pivot element, and pivot element will be placed in its proper position. Pivot element is placed in its proper position. For example, in this array, the pivot element we have told is 10. So 10 is placed somewhere here. It's the pivot element. And left side of the pivot element will be the elements which are lesser than the pivot element. And right side will be the elements which are greater than the pivot element. In such a way, we have to partition the array. For example, in this case, this 2, 1, 9 can be on the left side, and 15, 11 and 16 will be on the right side. So this order of these elements is based on the partitioning algorithm, but the left half of the pivot element will be the elements lesser than the pivot element, and right half of the pivot element will be the elements greater than the pivot element. So this pivot element is in its actual position. After sorted actual position, pivot element it will be in its actual position. Partitioning here means the finding out the proper place for the pivot element. So how we will do the partitioning? For that we can consider an example. So here it is shown that this first element is the pivot element. So while doing the partitioning of the in the quicksort algorithm, so all elements are left less than the pivot element will be kept here on the left side, and all elements greater than pivot element should be on the right side. So here after partitioning based on the pivot element, again the left side subarray is partitioned again based on another pivot element, and also the right subarray is also partitioned. So this process continues recursively. So here now we can see this is the algorithm for Quicksort. So mainly we have to focus on the randomized version of the Quicksort in the syllabus. But before that we should know what is the normal Quicksort algorithm. So for that we can consider one example. So suppose this is the array to be sorted. Array to be sorted 2, 1, 9. So we can consider another example. This is the array to be sorted. The elements are 7, 6, 10, 5, 9, 2, 1, 15, and 7. So this is the array. Suppose it is A, and we have to solve this array. So first element we will take as the pivot element. In this approach we will take the first element as a pivot element, and then remaining elements, the left side elements should be less than the pivot element, and right side of the array the elements should be greater than the pivot element. So we will keep two indices I and j. So this I value we will increment and j value we will decrement. So whenever we will compare the pivot element with the other elements. So if the left side elements, when we compare, if it is lesser than the pivot element, then we will increment the index I, because we need lesser elements in the left side. And whenever we find an element which is greater than the pivot element, we have to stop the incrementing. We have to stop the. And on the right side, what will happen is we have to decrement the j index whenever we find an element greater than the pivot element, because greater elements we need at the right side. So whenever we find the greater elements we will decrement, and whenever we find a smaller element than the pivot element we have to stop. So one I is stopped and j is stopped, then we have to swap both I and j. Then the values of the I and values of the both of the I stops, then values of these locations needs to be swapped. If I is greater than j, whenever I greater than j, that means this we are incrementing this I value, and whenever and decrementing the j value, and whenever that I greater than j, then swap the element with the pivot element. Swap pivot element with the j, the element in the position of j. New pivot element is in its appropriate position. So now we can, so here we can, in this example if we see, first we will compare the 7. 7 is the pivot element. 7 is compared with 6. 6 is lesser. Then, so we will increment I. Then it is compared with the element 10. 10 is greater than 7. So greater element means this incrementing of I is stopped here. and then we will start decrementing j. Decrement j if it is, so compare this 7. 7 is not greater than, it is equal to. So we have to stop here itself. Stop here itself. And then both I and j are stopped. So we have to swap. Swapping these values of I and j. So 10 and 7 will be swapped. Whenever this I value becomes greater than j, then we have to swap the pivot element with the value j. New. So now we can see the algorithm for this one, the partition procedure, and also for the quicksort procedure. So here this quicksort algorithm, quicksort, p is the starting index and q is the end index of the array. So here first we have to, if p less than q, the starting lower bound is less than the upper bound, then we have to find, first we'll find the position for partitioning, j. So partition of a is the array, then p and q plus 1 we are passing, then j is the position for partition, and that position we will place the pivot element, and then next we have to call quicksort recursively for the left half, p to j minus 1, and also for the j plus 1 to q for the right half. And now we can see the partition procedure. So in the partition procedure, if it is, here it is algorithm partition array, then the first element, and this is the last element, and we have to find the position of partition. So here the first element, which is considered as pivot element, it is stored in the a variable, and then this initial index value I is given as m, that the initial value, and j is given as the last value p. I is incremented using this repeat loop. I is incremented whenever a of I is greater than or equal to b. Then until a of I greater than or equal to b, which means a of I is incremented whenever a of I is less than b. That is, then next loop is repeat j equal to j minus 1. J value is decremented. Then a of j until a of j less than or equal to b. Whenever a of j is less than or equal to b, until means till that time a of j is this is decrementing is done. Instead of repeat loop, we can use another other loop, while loop or for loop also. So if I less than j, then exchange whenever both the indices I and j stops, then we have to swap. Then after that, whenever this I value becomes greater than j, that time we have to swap the pivot element with the element at the j position, a of j. Then return the j position as the partition position. So this is the algorithm for quicksort. The main procedure here is the partition procedure. And quicksort is a recursive algorithm. Now we can see the analysis part of the quicksort. The size of the input is specified by the number of elements we need to store. The basic operation here is a comparison. So here there are best case, worst case, and average case complexities. So in the best case, the complexity T of n, the best case of quicksort occurs when the problem sequence is divided into two equal parts on each recursive call of the algorithm. So best case, the value is 2 into T of n by 2 plus n. T of n equal to, best case complexity of quicksort is T of n equal to 2 into T of n by 2 plus 1 plus n. If we solve this recurrence, we will get, either you can use master method or iteration method. Once we solve this recurrence, we will get the value of T of n as n log n. That is, the best case efficiency of quicksort is n log n. And also we can see the worst case efficiency. Worst case efficiency of quicksort is this one, T0 plus T of n minus 1 plus n. And when we solve this equation, you will get T of n equal to n square. Worst case complexity is n square. So this is the quicksort. Now we can see the randomized version of quicksort. So where we have to introduce this randomness in quicksort, we have to introduce randomness while selecting the pivot element. while selecting the pivot element, we use the random number generator. So how to select? Normally the pivot element will be the first element, or in some algorithms they will use the pivot element as a last element. But here we can use the pivot element as a random number. So this is the randomized version of Quicksort. So worst case complexity of Quicksort is big of n square. The worst case behavior occurs when all the elements are already sorted. In this case, there will be only one element in one part and the rest of the elements fall into the other side. This can be avoided by a randomizer for the pivot element. The time taken by the randomizer is big of n log n. For very small inputs, time taken by the randomizer is comparable to the rest of the computation. So randomized version, if we use, the time complexity becomes n log n. So this is the randomized version of the Quicksort. So here R Quicksort, randomized Quicksort, then P and Q. So partition method is same. So only the change is here, that is while selecting the pivot element, this random function is used. That is random mod q minus p plus 1. So this is a random number generator. This is used to select the pivot element. And this random number generator, is used, and this one is used as the pivot element. And then, so this is the pivot element. Or the instead of first element, this is used as the pivot element, and this is the other element. And based on this one is passed to the partition, and then this partition procedure. All other procedures are same. Only the difference is random number generator is used to select the pivot element, and the pivot element is pivot index is selected from 1 to n, where n is the size of the array. Now you can see the analysis part of the randomized Quicksort version of Quicksort. If in each level of recursion, the split induced by partition puts any constant fraction of the elements on one side of the partition, then the recursion tree has depth. So if we consider the analysis using a recursion tree method, so the depth of one part of will become theta of log n, and big O of n work is performed at each level. So in the recursion tree approach, if we consider, then the maximum depth will be log n, and at each level there is big O of n work. Even if we add a few new levels with the most unbalanced split possible between these levels, the total time then remains n log n. Total time complexity of the randomized version of the Quicksort becomes n log n. If we consider the recursion tree method, we can understand that maximum depth of the tree is theta of log n. Then at each level, the computation cost is